property that some test that can be done. So he will prepare it in that state. Therein lies the rub. No experiment can prepare the state perfectly. There will be always some experimental uncertainties involved. Even it happens in our most elementary undergraduate experiment or high school experiment. When I want to measure g, the gravity acceleration due to gravity, by a simple pendulum, I will find that the length of the pendulum has certain uncertainty. If you keep a certain length and I keep one, and if I'm trying to measure distances accurately, say 10 to the minus 4 centimeters or 5 centimeters, I'm sure your length and my length may not match. The same way, the angle through which I'm making a move may not also agree. So when I do an experiment 100 times, then each time the initial experimental state may not be the same as before. This is one of the major problems with experiment. So when I do the theory, I do the theory for an ideal situation, a point mass and a string which is inextensible, and then there is a length associated with the right t equal to 2 pi into root L by g. But my L is uncertain. If I make 100 different pendula of what I think is the same will not be the same. So there is certain averaging to be done for this. The best example associated with modern physics is the polarization of light. Supposing the light is traveling along the z-axis, then there are two possible linear polarization of the light along x and y-axis. And supposing my experiment wants to say that have it polarized along exactly x-axis. Let me assume that the k component is undisturbed. I can also include that in my general theory, but right now let me just assume the k component is fixed. When I do an experiment and try to locate my polarization, how do I do that? I keep a Polaroid and then pass the light. But the Polaroid has a certain axis. That axis can be determined only up to a point. So when I do an experiment with several beams separately, then separately, if I just a minute, please. Then I have to take into account the experimental uncertainties also. This is what we normally do in classical mechanics, whatever I'm saying is valid both for classical and quantum. And this is done in a very general way using density matrix formulation. So let me now go to the board and start writing whatever I have said briefly. I will write it bigger. So this is done by the density matrix formula. This is the statement I want to do. The way I will do it is, I will use what I did earlier. I will be describing this quantum mechanically. This is an eigenstate of the operator sigma 3. We have already seen sigma z. This is what happens. Now suppose, think of it as when I do an experiment, I will have several qubits which will be formed, several of these states. Let me use the word qubit, or I can use spin systems, several spin systems every time. Think of an electron. Electron has spin half. So this is going, there is one electron gone, that has some spin. Second electron is another. And supposing I want to be prepared in one particular state, let me call it I. If I make a measurement of an operator O, quantum mechanically, this is the average of O bar I should get quantum mechanically. But experimentalists will have a difficulty in getting phi I all the time. He will produce phi I with certain probability. If I have n such systems, large of them, then he will produce it, say, m times. M may be very close to n. M divided by n is the probability he has produced that system. And the other n minus m, he would have produced the other state. I'm thinking in terms of only two states. So let me say phi I is one state, and the other state is the one which is orthogonal to phi I. Or you can even think of n systems, I going from 1 to n. So this is the probability. So now the prepared state I has probability Pi. Then the actual experimental result, when I do it in all of them, we'll have to average over this. So that will be summation over Pi, phi I. This is what the experimentalist will get. This is the quantum mechanical average. This is the average occurring because the experimental uncertainty that I have. That is my duster. So this can be written as summation I. If I am putting I going from 1 to 2, in this case 1 to 2, this will be O could be any operator. So I will write this as O I E I. Right? Which is Pi P1 O11 plus P2. Which I am going to write it in the following form. I am going to write this as trace of row O, which is row 1I, row 1I I1 plus row 2I. Remember, trace means adding the diagonal elements. What is that? Row O11 plus row O22. Row O11 is this, and row O22 is that. So I compare these two. So my row here has only one component. So row 1I is P1 delta I1. I compare these two. I get row 2I equal to P2 delta. So my row, the density matrix in this simple case is P1 0 0. This is the simplest form of the density matrix. Okay, so now let's make it a little bit more general. Let the state that I prepare be alpha is one state, which is summation over alpha I going from 0 and 1, and beta another state, summation j going from 0 to 1, beta j. Remember, I'm still using the notation I did 0 and 1 for the qubit. So when I put I equal to 0, I get this. I need not have alpha and beta orthogonal. The experimental cannot decide whether the state which is producing one may be spin up here and the next may be having a spin slightly off the z-axis which he is preparing. So they are not orthogonal. So this is the state he has prepared, and this is another state he has prepared. Maybe he has prepared gamma, delta, and so on. Right now, let me just concentrate on two of them. Okay. Then my density matrix becomes this. Average of operator rho. This is the full average, which I am going to write, is given by P alpha times the average of this operator here, alpha O alpha plus P beta Since I'm assuming there are only two kinds of prepared states by the experimentalists, P alpha plus P beta is 1. And these numbers have to be greater than 0. Kumar. These are probabilities. Any question in the chat mode? Nothing in the chat. Okay. Now I am going to substitute. These are orthogonal states. 0 is orthogonal to 1. So I am expanding alpha in terms of orthogonal states, beta in terms of orthogonal states. It is not guaranteed that alpha and beta are orthogonal. So now I write this average equal to P alpha. Okay, what is O alpha? O alpha is summation alpha I. And if I write alpha here, that will become J alpha J star. And summed over J. Let me rewrite that a little better. Alpha O alpha equal to sum over J alpha J, sorry, J alpha J star O sum over I alpha I. So this term becomes P alpha O J I. This is the operator O J I. I write it as sum over I J alpha J star alpha I O J plus P beta times sum. Exactly the same way. Exactly the same way, beta J star beta I O J. I'm going to pull this OJI outside, and the rest I will collect. The rest I'm going to write down as this part of it plus that part of it. I will write down separately. P alpha summation ij out here, and then P alpha alpha j star alpha I plus P beta. This is some more. Oh, I don't have to write that. P alpha P beta beta j star beta I O j. OJI is the same. And I'm going to call this object rho ij equal to P alpha alpha I alpha j star plus P beta beta I beta j star. So this becomes summation over ij rho ij ojr. But j is summed here. So this is nothing but summation I rho o I r. So this is the sum of all the diagonal elements of the product matrix rho o. So this is nothing but trace of rho o. And rho is this.
I have a question. Hello.
Rho describes the experimental state of X. Let me take specific examples of rho, and then you'll see what is happening.
I have a question. Can I?
1 minute. Yes.
You have started with alpha, beta, and you have done this. You have arrived at this final.
Did I make a mistake? Let me just see.
No. I'm not saying that. I'm asking a question. No mistake.
Yeah. What is the question?
See, you said that some other time there could be a different beta. So you at some time initial state may be alpha, some other time it may be beta, and so you have constructed this.
Yeah. The experimentalist will here I am asking him to prepare in the state alpha.
Correct.
Alpha could be a general state, spin state.
Yes.
But so, the experimentalist will not be able to prepare it in the state all the time.
Yes, sometimes they will have alpha, sometimes.
So he will have alpha here. He will prepare it in alpha with probability P alpha.
Yes.
And he will prepare it in the state beta with probability P beta.
But some other time I may have some other gamma instead of beta.
Pardon?
At some other time, instead of.
This is in a beam. So, for example, this is the property of the beam he has produced.
Yes.
If we are thinking in terms of electrons, he has produced a bunch of electrons.
Yes,
say
exactly.
1,000 of them.
Correct. What so I want to know
that
is
thousands property. The next 1,000 he prepares, if it is identical, it should be having the same density matrix. If it's large enough.
My question is, can there be more terms in this summation alpha, beta, gamma?
Oh, he could have produced in gamma also.
Yeah.
Which will be
so can we have more?
State.
Is the number of terms restricted
then
to
I will add up P gamma there.
So we can in principle have more terms. Is that
right.
correct?
No, it will not have. This will be a two. Essentially, this will always rho will always be a 2 by 2 matrix.
That is correct. But number of terms in that average, P alpha, average in alpha, then P
so
beta.
How do you go about determining P alpha, P beta, P gamma will be a question.
Yeah.
That will be answered.
Okay. Fine.
How does one go about doing that?
Please continue. I'll come back later.
Okay, good. So given a beam, how do I know what state he has prepared it in? Okay. There is always an ambiguity because there are two different answers which can give the same experimental value. Okay. But once I have fixed my density matrix, for any other operator, I will get the same answer for both of them. So just by looking at the experiment, I will not be able to uniquely determine the density matrix. This is an issue. But I will tell you how to determine it and the non-uniqueness occurring in it. Okay. Hello.
This is okay. Fine. Please continue.
All right. Now I've written down my rho. So let me write down my rho again. Rho was P alpha, alpha I, alpha j star plus P beta, beta I. Okay. Now, I have prepared it in the state. So let me write this as very clearly. It will be P alpha 1, alpha 1 squared, alpha 1, alpha 2 star, alpha 1 star, alpha 2, alpha 2 squared, plus P beta, beta 1 squared, beta 2 squared, beta 1, beta 2, beta 1 star. This will be my full beta, which when I can write it, the 2 by 2 form, alpha 1 squared plus P beta 1 squared. Excellent. Notice, P alphas are of course real numbers. These are complex conjugate of each other. So rho is Hermitian. What is trace of rho? Trace of rho is the sum of these two. So let me write that out. Trace of rho equal to P alpha squared, P alpha. I have written down alpha 1 squared here. So similarly, I would have had P alpha, alpha 2 squared plus P beta, alpha beta 2 squared. So I would get alpha 1 squared plus alpha 2 squared plus P beta, beta 1 squared plus beta 2 squared. But what is alpha 1 squared? Alpha is normalized.
Excuse me, sir.
So alpha 1 squared plus alpha 2 squared is 1. So this is 1. So this becomes P alpha plus beta, but P alpha plus B beta is 1. Okay. All right. Now, if my prepared state is an eigenstate of the operator O, the one which I am measuring, everything will be diagonal. There won't be any non-diagonal part. Now I want to discuss it a little bit more in terms of spin half a system at some length. Incidentally, what Professor Ashok Kapoor asked is a very active area of work. It's called retrodiction of density matrix. It is very important in information theory, quantum information theory, because what you can actually measure is the density matrix. So the question arises, how do I know what the experimentalist prepared? Can I say he could have made two different preparations and get the same density matrix? Answer is yes. It may not always be possible. There are cases in which it will be I will also, we'll see when it's possible and when it is not possible in some simple cases. Okay. Now I'm ready to make a general thing. I've already indicated two properties of the density matrix. Rho is Hermitian, trace rho is 1. Okay. Now we have the following situation. Since rho is Hermitian, it can be diagonalized. So diagonal form of rho by unitary transformation. This must be a real number, which let me call it Q1 0 0 Q2, and the trace Q1 plus Q2. Trace is reserved is 1. Let me go back and do the experimental again. Suppose the experimentalist says he is perfect, so his P alpha is 1 and P beta is 0. Pardon? Okay, I will explain again. Original state I had was P alpha, alpha, alpha. This is the state he prepared. Alpha was prepared with probability. Please say that again.
Sir, nothing, sir. Participants, please mute your mic.
Ashok, can you please put it in chat mode? Why P alpha, P beta are non-zeros? Oh, no, one of them could be 0. Need not be both. Their summation is 1. And they are greater than 0. So that's the case I'm considering now. Yeah. This is possible. The other alternatives, or this is also possible. The experimentalists prepared all the states in beta. Maybe. Okay. This is possible. We will analyze both of them. So in the first case, I will get my rho would be P1 alpha 1 squared. P1 can be just 1, alpha 1, alpha 2 star, alpha 2 star, alpha 1, alpha 2 squared. And remember, alpha 1 squared plus alpha 2 squared is 1. And this you can check has determinant 0. So one of the eigenvalues is 0 and the other eigenvalue is 1. So the diagonal form is 1 0. And rho would be this. And rho diagonal would be fine. Till now, this is a situation I can have. So if I had one of them, rho diagonal will be always in that form. And rho squared diagonal will be, if rho were P1, P2, P1, P Q, P alpha, Q alpha, sorry, P beta, or let me write, no, P alpha. That's my test. Let me continue here. If rho d for any one of them is some number here R1, R2, 0, 0, R1 plus R2 is 1. This is coming from some rho, U, rho, U dagger. This is the density matrix which the experimentalist gave me, and I diagonalized it and got some mathematical formula, rho d. I can take his rho, write rho d squared rho. What is rho d squared rho? Rho d squared rho is rho u, u dagger, u, rho, u dagger. Notice u dagger is 1, so I can write it this form. So this is nothing but rho d squared, which is R1 squared 0, 0. Notice trace rho d is 1. Trace, this is R1 plus R2. You have already verified that. Trace rho d squared is R1 squared plus R2 squared. Since R1 lies between 0 and 1, can you please put it in the chat mode, please? I will appreciate that. It is easier for me to follow because if the voice coming through is having it's getting messy.
No, sir, I muted. He is talking with someone.
No, let him say it, please, because these are important points. I'm willing to spend 5 more minutes or 10 more minutes in explaining this.
Sir, please continue, sir. He is. I muted him, sir.
I see. Okay. Since it is so, if R1 is less than 1, then R1 squared is less than R1. R1 squared is less than R1. Because if R1 is less than 1, when I multiply R1 by R1, it becomes less than 1. So this will be less than 1. R2 will also be less than 1 if R2 is, supposing these numbers are 0.9 and 0.1. This will become 0.81 plus 0.01. So this will be less than rho b. Trace rho b. When will the two be equal? R1 squared plus R2 squared equal to R1 plus R2. When can this happen? When I take it this side, I get R1 into 1 minus R1. I bring it here, equal to R2 into 1 minus R2. No, I shouldn't do it this way. How do I say it? Yeah, R1 into 1 minus R1 is equal to
R1 square minus R2 square.
just a minute. Just
on
a
one
minute.
side.
R1 squared plus R. I want to show that this is only when R1. Okay, R1 into 1 minus R1 plus R2 into 1 minus R2. Correct? This I'm taking, if suppose this is less than 1, it lies between 0 and 1, both of them. So this number is positive. This number is positive. This cannot happen. Unless both of them are 0, this equation is not possible, right? Either this is 0 or positive, either this is 0 or positive. So the only solution to this problem is that each of them must be 0. This means R1 is 0, R2 is 1, or R1 is 1, R2 is 0. So the two to be equal, it has to be having only a single state. That is, my row should be in the state 1, 0. So this means for trace rho D, rho equal to trace rho squared, the system must be in a single quantum state. I will repeat the proof of this again so that you see it. This is called a pure state. If rho D trace rho is greater than trace rho squared, then it is called a mixed state. It is not expressed as a pure state. It is a mixed state. So now let me understand how this whole thing works. Let me just go back to the statement I had made earlier. If beta were 0, that would correspond to the pure state. Let us see how. What was rho when beta was 0? It was, and P1 was 1. I had the equation P1 and P alpha, prepared the state alpha, and P beta was the state beta, probability. If I just put P alpha equal to 1 and P beta equal to 0, I have produced this pure state. I have no mixture at all, nothing. But when I have this number as say 0.8 and this as 0.2, I am producing 80% of alpha and 20% of beta. That's what is a mixed state. Is it okay? All right. If this is a mixed state, now let me work out the most general density matrix for a 2x2 case. Rho 2x2 most general density matrix. Rho is Hermitian matrix. Yesterday we discussed in a 2x2 how many most general Hermitian matrices we can write. 4. So this is something I had done yesterday. I will write it this time as P0i plus Px sigma x plus Py sigma y plus pz. And I will use the fact that trace of sigma x squared equal to trace sigma y squared equal to trace sigma z squared equal to 2, and trace sigma I sigma j is 0 when I is not equal to j. So how do I locate my px? Px, or firstly let me start with p0. Take trace of p. Trace of sigma x is 0, trace of sigma y is 0, trace of sigma z is 0. That also I should write. Trace sigma y. So when I do that, I just pick up p0 times trace of y. Trace of y is 2, so this is 2 p0. So this expression that I have is trace rho. What about px? Px is half of trace rho and so on. So let me write down my rho completely, equal to half trace rho plus trace rho sigma I for every one of them times summed over I. So I can let me write one more step so that it becomes clear. Trace of rho sigma x for px, and of course I have sigma x plus trace rho sigma y plus trace rho sigma z. These are the elements. So now let us write out how this looks like in a 2 by 2 form. So rho is of the form P0 plus P3, P0 minus P3, P1 minus IP2, P1 plus. So what are the eigenvalues of these? So that when I write it in the diagonal form, you will immediately see. Let's find out the eigenvalues. That's very easy to find out. Sum of the eigenvalues is 2 lambda 1, 2 p0. The product is the determinant. Determinant is, notice, p0 squared minus p1 squared minus p2 squared minus p3 squared. So if I call this P1, P2, P3 as lengths, I will just trace rho is this. Okay, so let me write it down. Find out lambda 1 and lambda 2. I square this. That gives me 4 P0 squared. This I will write P0 squared minus P squared. I will treat P1, P2, P3 as a vector. In space. So this is 4 P0 squared and lambda 1, lambda 2 squared 4, if I write, will be 4 P0 squared minus P squared. So I subtract these two, I get lambda 1 minus lambda 2 squared is equal to 4 P squared. So from both of this, I get lambda 1 plus lambda 2. They all have to be positive, 2 P0, and this is lambda 1 minus lambda 2. So I get lambda 1 equal to 2, no, P0 plus and lambda 2. Now, let us see when will it be mixed or when it will be pure. That can be checked by doing the following, right? Squaring this, one of them should be 1. When can that happen? When P0 plus P equal to 1 and P0 minus P plus PC. So this means P0 equal to P. And if P is less than half, you can verify that it is a mixed state. This is the pure state. Now let me, just 1 minute. I will take only 1 minute more, answer the question which was posed. It was this. Suppose I had a state rho. The density matrix was 1 half. How can I produce this? I can produce this state in the following way. I can write half 0 0 plus half 1 1. Check this. This is half 1 0. Sorry. 1 0 0 1 plus half 0 1 0 1. I can multiply this out. This gives me, did I write it correctly? This gives me half 1 0 0 0 plus half 0 0 0. So, if I make a measurement of sigma x, sigma z, these are eigenvalues of sigma z, I will get half the probability in one for 1 1 and another one half. If I had a state like this and there was a beam of n particles, I will find half of them in this state and half in that state. So I will conclude the answer is this. So I will say the experimentalist prepared it, half of it in sigma z equal to +1 and the other half in sigma z equal to -1. But let me also look at the other one. 1, 1, 1 by root 2. This is eigenstate of sigma x. I had written down this yesterday. And now let us combine it. 1 by root 2 with half here. 1, 1, 1, 1 with another root 2 plus 1 by root 2, 1 minus 1, 1 minus 1, 1 root 2. So I can add this. This is equal to half. I will pull out this 1/4, and that is 1, 1, 1, 1 plus 1 minus 1 minus 1. So when I add all that, I get 1 by 4, 1 by 2, 1, 0, which is the same as over here. So if I make a measurement of sigma x, I will find half the time here and half the time here. So I will come out with the same answer. So the experimentalist cannot say that the state was prepared with half along sigma x and half along along z and half along minus z, or along plus x, half minus x. Similarly, you can do the calculation with y. It shows that there are several possible solutions to a particular density matrix. But having got a density matrix, any other experiment that you do will be known, the value will be known. What does it mean? Different preparations by experimentalists due to some error or some difficulty. If it gives me the same density matrix, there will be no way in which I can distinguish it. So that is the formalism. There is much more to it than this. This plays a very important role when we discuss entangled states. And that is part of serious work on these days going on, both in information theory and understanding quantum mechanics better. Okay, I think I will just stop here for today, and that's it. And all the best for all of you, and I hope you're able to pursue physics with some serious interest and communicate this to all the students. I wish you the best.
Yeah, thank you. Thank you very much, Professor, for an interesting matrix formulation.
Yeah.
In a simple way, easy to understand.
Okay.
Audience, do you have any queries?
Sir, very excellent presentation, sir.
Sure.
How we
Yes.
can relate physics with this density matrices, sir?
How can I?
How can we relate this density matrix in physics, sir?
Please, can you put it in the chat mode, please?
Sir, that professor is asking, how can you relate this density matrix into
Physics.
physics?
Physics, sir. Yes.
Physics of?
No, how you are relating this into physics, he is asking.
No, the physics is that unless if I want to do anything with experimental work, then this you need to know what is the actual experimental preparation. That has to be characterized. So without that characterization, we cannot proceed. So this actually became very important in optics, because when I produce a beam in optics, it is never clear to me whether I produced it with perfect polarization or with some, after all polarides have their own defects. Nothing is perfect. So how do you characterize that? So you do an experiment, I do an experiment, so we have to check.
Okay, thank you. Thank you, sir.
But this is just an introduction to density matrix. There is, of course, much more to it than this. And I just sort of introduce you this way.
Okay, Professor. Thank you.
All right. Then
I think so. Tomorrow morning, first 2 sessions, lecture will be given by Professor Sridhar, Chennai Mathematical Institute, Chennai. Then afternoon 2 o'clock we have a valedictory function.
Right. He is planning to give lectures on Feynman path integrals.
Okay, sir. Tomorrow morning, sir.
Yeah, 10 o'clock. Unfortunately, I cannot be there because I have a class. All right.
Okay, sir. Okay, sir.
Okay.
So can you please join in the valedictory function in the afternoon?
Sure. That's at 2 o'clock, you said.
Yeah. Professor Kapoor, sir, you can also join, sir.
Yes, okay. Thank you. I will join.
Yes, sir. Yes, sir.
All right, good.
Thank you, sir. Thank you so much for professors. We have such an excellent lectures for the past four days. I think definitely it will motivate our students to do the theoretical research work in their future careers, sir. Sure.
All right, sir. Okay, bye.
Thank you. So can we end up today's session, sir? Can we wind up today's session, Professor?
Yes, please.
Yeah. Thank you. Thank you so much, participants. Tomorrow morning at 10 o'clock, we have the first session. That is the last day.
Okay.
Thank you, sir. Thank you. So the attendance link for the today's session will be shared in the WhatsApp group. Thank you. Now I'll end up the today's session. Thank you. Thank you.